The lesson of today is the continuation of the orbital maneuvers. We need to discuss only one argument, that is the generic transfer orbit, a maneuver occurring between two orbits in the plane, generally elliptic, but having different orientation and size. And at the end of the lecture, we will run two exercises together. Here we have two generic elliptic orbits, those intersect in 2 points. We have two possible single bar maneuvers and many two-bar maneuvers by using a transfer orbit. Let's see here first how to manage the single bar one. This problem we can solve graphically by representing the orbit in a plane and finding the intersection points. But here we want to solve it analytically in order to learn the algorithm to be implemented eventually in a program. Given are the geometrical data of the two orbits, we call the starting one red and the target one green. Moreover, we choose the axis x oriented along the periapsis of the red orbit, and the periapsis of the green one is forming the angle eta with the first one. When the orientation is known, there remain only two parameters each orbit. We choose here the angular momentum and the eccentricity of each orbit. Task is to find the position of the intersection, also radius and angle theta, the two velocities, and the delta v. Actually, there are two intersection points, and we need to find both. By means of the trajectory equation, we can express the radius as function of the angle. Important to remember that the angle θ1 and θ2 are starting from the periapsis of the corresponding orbit. Then, since we look for a common point, we can put the radius of the conic 1 equal to the radius of the conic 2. And by replacing θ2 into θ1 minus eta, because we know the relative position of the two periapses, we can get a unit equation in the variable θ1. And this equation is a trigonometric one that we can express in the form alpha cosine θ1 plus beta sine θ1 equals gamma, where alpha, beta, and gamma are constant values displayed in the bracket. This equation we can solve either numerically or analytically. The analytical solution is possible by replacing the trigonometric function cosine theta and sine theta with the variable t equals tangent of theta half and using the identities here displayed. In such a way, the equation is not any longer trigonometric but algebraic. We find a quadratic equation solvable with the standard formula. We notice that the solutions are 2. And when we revert to the trigonometric function, we get two angles equal to the twice of the inverse tangent of such t values. When θ1 is found, then also r is given from the trajectory equation. The components of the velocities we can get from the formulas here displayed, using the angle θ1, the eccentricity E1, and the common radius r. We do for the velocities of the two orbits. In this case also θ2, E2 are needed. And the delta v as vector we can obtain by subtracting the corresponding components, and its modulus is then the square root of the square sum of each component. We repeat the same procedure for the second angle, and we choose the most convenient delta v. This exercise we will run in Geogebra directly, also using a geometrical method. It solves the same problem shown before. Given are the central body, the parameters of the two orbits by means of P and E, and the angle between the periapses of the orbits. By means of the program, we build the two orbits whose parameters are known. The red one is the starting orbit and the green the target one. Then we find graphically the intersection points They are two, and for each one we calculate the velocity modulus using the bis viva equation displayed on the left side, for the red and for the green one. And in order to find delta v, we need to build the velocity triangle. Each velocity vector is built in such a way. The modulus is calculated as we have seen. The direction is given by the tangent of each orbit. And the tangent is found graphically with the program. Eventually we get 1640 meter per second and 1670. They are similar, however, but the first intersection point is more convenient for the maneuver. The second exercise uses the same data of the previous one, but with a different method. This time we are looking for a dual bar maneuver to see if the delta V is less or not. The dual bar maneuver requires a transfer orbit. Let's see how to choose it. Once represented the two orbits, we need to find a third one, that is tangent to both, and there are many possibilities. One of them is to build an ellipse that is containing both, like in the picture. Then we find the two tangent points, and for each one we calculate the velocity of the starting conic and the one of the transfer conic by means of the bis viva equation, as displayed. For the velocity of the transfer conic, we need to know its semi-axis A, but this is given by the program. And since the velocities are parallel, the delta V is simply their difference. We repeat the procedure for the destination conic, and eventually we find delta V equals delta V1 plus delta V2, 1088 meter per second. Definitely, the dual bar maneuver is more convenient. Thanks for your attention. See you next time. Bye bye.